mathematicians, we'll see one more linear algebra problem from CSIR. It is a very interesting problem in the sense we're going to solve this problem just fully geometrically. Okay, so it is in that sense it is very interesting. So once you understand the geometry, this problem you can just answer by just once you look at the matrix you can answer the problem. So let's see how to visualize matrices and how to visualize its action on the Euclidean space. That is what this problem is about. Let's see the question. For a matrix A as given below, which of them satisfy A power 6 equal to identity? Okay, so 6 times if you act A on a vector, you should get back the vector. That's what it means to say A power 6 equal to identity. Okay, now there are four matrices are given, but they are in some particular form. You see these numbers are cos and sine is given, and there is a row and a column with the exactly 1 and other 0. So that is the case in every matrix. Okay, so this is some particular peculiar kind of matrix. So since these numbers are trigonometry functions, so you can actually guess that this should be a rotation matrix. Okay, so once you guess it is a rotation matrix, then pretty much the problem is solved. So let's do it step by step. Okay, now you consider this matrix A. It is a 3 by 3 matrix. In a 3 by 3 matrix, so 3 by 3 matrix means we know that it is a linear transformation from R cube to R cube. Okay, for R cube there are three basis elements E1, E2, E3. If you look at a 3 by 3 matrix, then the first column is nothing but image of this vector under the matrix A. So this is nothing but A E1. So remember that A is, even though it is a matrix, it is also represented as a linear transformation T from R cube to R cube. So T from R cube to R cube. So this matrix represents the linear transformation T from R cube to R cube. Then this first column is the image of E1 under the linear associated linear transformation. This second column is the image of the second basis vector E2 under this linear transformation. Again, third column is the image of E3, the third basis vector under the linear in the linear transformation T. That's how we form the matrix of a linear transformation. Okay. Now, in each of the given matrix, you see, so third column is the, what we are saying, it is an image of E3, and what is image of E3? It is E3. That is again, this is again the third basis vector. Therefore, this matrix satisfies A of E3 equal to E3. Now, if you look at this matrix, this is image of E1. Image of E1 is again E1. So, A of E1 equal to E1. Now, second column is the image of E2, and what is in the place of second column? Again, that is E2. Therefore, A of E2 equal to E2. Here, A of E3 equal to E3. So, what is happening is this matrix takes the third basis vector to third basis vector. This matrix takes first basis vector to first basis vector, and so on. Now, let's make some small computation. For example, suppose A of E1 equal to E1. Then we look at a vector from the real line in the three-dimensional Euclidean space. Okay, if it is coming from the real line, then only it will have x coordinate. Okay, and the remaining other to the 0. I can show you in the image. For example, you look at this image, you assume that the red color arrow, that is the x-axis. Okay, and this green color arrow is the y-axis, and the blue one, this blue color arrow, that is the z-axis. Okay, now if you look at any point on the x-axis, it will be of the form alpha 0 0. Since the point is on the x-axis, its y coordinate is 0 and z coordinate is 0. Now, suppose if A takes E1 to E1, let's see how A act on. So, you note that the point 1 0 0. For example, this is the point. This is our E1. E1 1 comma 0 comma 0. This is our E2, 0, comma 1, comma 0, and this point is our E3, 0, comma 1, comma 1. We are saying that the matrix A takes this point, this red color one, that point to itself. Suppose it is the case, we look at the any point in the x-axis, we claim that that point will also map to itself. So once a linear transformation takes this point to itself, that 1, 0, 0, we claim that any point in the x-axis will also map to itself. Okay, point wise. So that is what we are claiming here. Now, so A of alpha 0, 0 equal to alpha 0, 0 can be written as alpha times 1, 0, 0. A is a linear transformation, so scalar comes outside. So A of 1, 0, 0, A 1, 0 is again 1, 0, 0. You take back the alpha inside, you get alpha 0, 0. So we get if A of E1 equal to E1, then any point in the x-axis is fixed by A. Okay. That is our first observation. Similarly, if a of E2 equal to E2, okay, then y-axis. So if this point, this green color one point is fixed, then full y-axis will be fixed by the matrix A. Okay. Similarly, for a of E3, if A of E3 equal to E3, then the entire y-axis will be fixed by the matrix A. Okay, that is proof is exactly similar. Okay. Now we assume that suppose A of E3 equal to E3. Okay. Then A of E3 equal to E3 means what we know, this point 1 comma 0, this point 0 comma 0 comma 1. This point is 0 comma 0 comma 1. This point is fixed by the matrix A. Once it's fixed by the matrix, then we know that I'm sorry, we know that full z axis is fixed by our matrix A. Now, so we look at these planes. You see, now this as I said, this is x-axis, this is y-axis. So there is this brown color plane. Okay, that contains both the axes. So that plane is nothing but z equal to 0 plane. Okay, so if you take any point here or here in this brown color plane, the coordinates z coordinate will be 0. Now again I am going one step above, then there is a plane that passes through this point 0 comma 0 comma 1. So so this blue color plane, this plane is not passing, this plane is not passing the z axis at this point, but it passing through z axis at this point. Okay, now if you take any point in this blue color plane, its z coordinate will be 1. Similarly, if you take any point here or here in this orange color plane, you will get z equal to 2. Okay, similarly here z equal to 3, z equal to minus 1 here, z equal to minus 2. So any point, arbitrary point, you will satisfy this condition. Okay, so here any point is of the form x comma y comma 3. Here any point is of the form x comma y comma 2. Here any, this blue color plane, any point is of the form x comma y comma 1, and x and y can be any real number. Okay, so since it is a plane, it is two dimensional, x and y both varies. Okay, so we're going to get a geometric picture of the action of the matrix A. Now I take a point in the plane z equal to alpha. Okay, so z equal to alpha, so if alpha is a positive number, then it will be some plane here. If it is a negative, alpha is negative, then it will be a plane here. Okay, some one of this, like some plane like this. Okay, z equal to alpha, the const z coordinate is constant. Okay, now in any such plane, every point is of the form x comma y comma alpha, and I look at the image of that point coming from this plane with the matrix A. Okay, so you notice that this A takes E3 to E3, therefore we have E3 here in the third column. Now what is the image? We do the formal calculation. We get if you multiply, we get this matrix times this vector equal to x cos pi by 4 plus y sin pi by 4 minus x sin pi by 4 plus y cos pi by 4. This row into this column will give me alpha. Okay. Therefore, what we see is, if you take a point from z equal to alpha in the three-dimensional space, then its image under the map, under the linear transformation A, again having z coordinate alpha. So what we are observing is each of this plane, you take a point here, and you apply the linear transformation A, you get a point again here only in the same plane. Okay, but we have an assumption. We have assumed that if A of E3 equal to E3, okay, if the z-axis is fixed, if the z-axis fixed by the if the z-axis is fixed by the linear transformation, then you take any point in the plane z equal to alpha, its image is again a point in the z equal to alpha. Okay, so basically if it is a arbitrary linear transformation from r cube to r cube, then image of this point can very well go here. Image of this point can very well go here. Okay, but since this satisfies a of e3 equal to e3, we have proved that if you take a point from z equal to alpha, the plane, then its image also will lie in the same plane. Therefore, each of this plane parallel to xy plane, each of them are invariant under the matrix. So invariant means that this plane goes to this plane only. This plane goes to this plane only. So a point in this plane cannot go to the some other plane. Okay, it will be, this point will go to some other point in this plane only. So that is what we have proved here, because once you, when you act this matrix on a vector, this alpha remains as it is. Okay, now therefore each of those planes are invariant. Now we look at how this 2 by 2 matrix acts on x comma y. Okay, now we know that the each of this plane is invariant, so we look at the action on a two-dimensional plane. Okay, so a two-dimensional plane means only there it will have two coordinates. So for example, we look at z equal to 0 plane. Okay, z equal to 0 plane is basically xy plane only, so it will have only two coordinates. Now if I act it on some xy, we get this answer: x cos pi by 4 plus y sin pi by 4 minus x sin by 4 plus y cos pi by 4. Okay, so now we see how to visualize this action. So we we take this vector xy to be 1 comma 0, then we get so image of 1 comma 0. So 1 comma 0, you see it is a point in the x-axis. I look at the image of 1 comma 0 under this matrix. I get cos pi by 4 minus sin pi by 4. Cos pi by 4 minus sin pi by 4 is equal to 1 by root 2 minus 1 by root 2. Therefore, under this matrix, this point is mapped to this point. Okay, so what is happening? This point is rotated 45 degree. What is this 45 degree? This pi by 4. So pi is 180 degree. So pi by 4 is 45 degree. So we get this point is rotated to this point 45 degree. Okay. Similarly, we look at where this point 0 comma 1 goes to. You see 0 comma 1 goes to 1 by root 2 comma 1 by root 2. 1 by root 2 comma 1 by root 2 is a point here, and so how much it is rotated? It is 45 degree. Okay, so I mean here you see this 45 degrees larger than this 45 degree, because that I didn't draw the diagram quickly, I mean sorry, correctly, but in principle, I mean if you draw the diagram properly, it should be somewhere like this. So this should be the 45 degree. Okay, so whatever what we are observing is this cos pi by 4 sin pi by 4 minus sin by 4 cos pi by 4. This matrix is a rotation matrix. Rotation means there are two types of rotation is possible. One is clockwise rotation, another is anti-clockwise rotation. But with this example, we observe that it is, this matrix is a rotation by pi by 4 or 45 degree in the clockwise direction. Okay, so what we are concluding with these two observations: each of these planes are invariant under the action of matrix A, any matrix A satisfying A E3 equal to E3, and inside each of this matrix, the matrix going to act only by these 2 by 2, because Z is constant. then every point here is going to get rotated. This point is going to rotate in this plane, this point going to rotate in this plane, this point going to rotate in this plane. Each point is going to rotate in this plane. Rotate by how much angle? The angle is given by this, whatever the degree. So in this example we have pi by 4. Okay, now you see here, if a of E3 equal to E3, then we look, then the planes which are the planes z equal to alpha is invariant. Okay, so if a of E3 equal to E3, then z equal to alpha, these planes are invariant. If a of E1 equal to E1, then the planes x equal to alpha are invariant. Okay, so here the planes y equal to alpha is invariant. Here the plane z equal to alpha is invariant. So the proof is exactly same. So here we proved that if a E3 equal to E3, then the plane z equal to alpha is invariant. The same proof. Okay. Therefore, what we are observing is, so I mean, if this problem is asked in interview, and if you are giving this kind of geometric explanation, so you can just impress the people with just one this answer. Okay. Okay, now what we are concluding, so if you have E3 equal to E3, then you have to look at the Z equal to alpha, this various Z equal to alpha planes. But if A of E1 equal to E1, then you have to look at x equal to 1, x equal to 2, and so in that case, so that plane will be will be perpendicular to that. In Okay, so that you can imagine how x equal to 1, x equal to 2 looks like. Okay, and in each, so basically because each of these planes are invariant, in those planes it going to act by rotation. Okay, this is rotation by 45 degree, rotation by 60 degree, rotation by 30 degree, rotation by 90 degree. So you want a point to come back to itself, right? A power 6 equal to identity means if you apply the matrix 6 times, you will get the same point itself. So the point will each time when you apply A, the point will get rotated. When you apply 6 times, the point should come back to itself because it is an identity matrix. So for what angle of rotation, after you rotate it for 6 times, you will get back to itself. So basically you have to rotate something in the plane 360 degree, then only the point will come back to itself. Okay, this point you have to rotate it 360 degree to come back to itself. Therefore, if so this pi by 4 is 45 degree, 45 degree if you rotate 6 times, what will you get? uh, 45, 90, 180, 270 degree. So in 270 degree you won't come back to the starting point. But if it is a 60 degree, then 6 times 60 degree you will get back the original point. Okay, so therefore this is the second option is the right answer. Okay, so once you understand this, then you can geometrically see what this matrix is doing. So basically this matrix takes preserves each of the planes x equal to alpha, and in each of those plane x equal to alpha it is act by rotation by 60 degree. Therefore if you apply this linear this matrix A 6 times on any point of the plane x equal to alpha, you will get back the point. Therefore a power 6 will be identity. Okay. Okay guys, I hope you understand it clearly. And again, any if you have any doubts, do let me know. And so there is some nice software I forgot to mention. This is called 3D calculator, GeoGebra 3D calculator. That's where I got this very nice image. There you can actually rotate this diagram and see the image very clearly. So please download it for in your cell phone or a laptop, anything. It is available. Please check 3D calculator, GeoGebra 3D calculator. Okay. Okay guys, have a good day. Take care. Bye.